Welcome back, everybody. In our last video on closed sets, we finished by showing that a set was closed if and only if it contained all of its limit points. And I also had alluded to the fact that limit points are called that because they're really the limits of certain sequences. So we're going to start this video by writing down a theorem that makes that precise. So the name of the theorem is that limit points of sets are limits of sequences. Okay, so what's the setup? Well, we have some subset, S and R, and then we have some element, A and R. Okay, so we want to know whether or not A is a limit point of S. And the answer is going to be A is a limit point of S, so it's in the set L of S, if and only if there exists what I'm going to call an S sequence. So this means a sequence whose output, remember a sequence is a function whose domain is the positive integers, and we only want ones whose outputs are in S. Okay, so it's a sequence whose terms are all elements of S. Okay, and so the claim is that A is a limit point of S if and only if there exists an S sequence that converges to A. So you can take points in S and let them to converge in A. And furthermore, we're going to assume that this sequence we choose, it doesn't consist entirely of points of A. In fact, eventually there are no more A's. Okay, so there exists a sequence, an S sequence that converges to A, and which eventually does not equal A. Okay, so you don't want any of the terms. Okay, so what we'd say is, so if you had this sequence A dot converging to A, you'd want it to be the case that AN does not equal A for sufficiently large N. Okay, what do I mean by sufficiently large N? I mean in a tail. Okay, so for N, at least some big N. Okay. So we go to some tail, and then all of a sudden it doesn't equal. It's okay if it happens early on. That's not a problem. You can essentially toss that stuff out. But eventually we want it to be really different. Okay, so let's give a proof here. So let's start by assuming that, well, we have a limit point, right? So if A is a limit point of S, then, well, what did it mean to be a limit point? So to be a limit point, it had to be the case that every punctured A coin, okay, so remember that's an A coin where we get rid of A, has to contain an element of S. Okay, every punctured A coin. So I want to write down a specific collection of punctured A coins. Okay. Then the punctured A coin, where I take A and I get rid of 1 over n, and I take A and I add 1 over n, but I throw out A. This punctured A coin contains an element which, since this is based on this little n here, I'm going to call it A sub n. Okay, well that's clear that it contains such an element, but the issue is it contained in S? And if we were talking about a limit point, then there must be some element in this punctured A coin, which is also an element of S. All right, and already I now have a sequence, all right? So define a sequence A dot equal to the sequence AN, n at least 1. Okay, now what is my goal? My goal is to show that this sequence A dot actually converges to A. Because what will I have then done? Well, first, I've actually built a sequence of elements which are in S, so it's an S sequence. If it converges to A, cool, I've hit the second bit. And it said which eventually does not equal A. In fact, I can get that it doesn't equal A ever because we've chosen all these ANs in this punctured A coin. Okay, so that's excellent. So we just need to show now that this sequence converges to A, which means that every A coin contains this tail of this sequence. Okay, so we need to show every A coin contains a tail of this sequence A dot. All right, fine. Fine, we want to take an arbitrary A coin, so we'll let epsilon be greater than 0. Fine. There's 0, there's epsilon. By the Archimedean property, I know I can choose a large enough positive integer so that 1 over n is our positive integer, is less than epsilon. Okay, so by the Archimedean property, median property, there exists some positive integer n, and of course it depends on epsilon, right? So we could say n or n of epsilon, so positive integer, such that 1 over n, of course, which is positive, is less than epsilon. Okay, but that would tell me now, because 1 over n, forget the a minus here, just to look at 1 over n, this is a decreasing sequence. So if I increase little n, then 1 over little n gets smaller. So thus, if little n is at least as big as big N, then 1 over little n is less than 1 over big N. Of course, it's still positive. And because we just established 1 over big N is less than epsilon, well, it's still true over here. So what does that tell me about a little n? Hence, well, a little n, we know that is in the a coin a minus 1 over n, a plus 1 over n, which is certainly now contained in the coin a minus epsilon, a plus epsilon, because we're looking at a bigger coin, right? So here I have my little 1 over n. That's my 1 over n coin. There's negative epsilon. There's my epsilon coin, right? 1 over n coin, really tiny. Epsilon coin, comparatively big. So this is a subset, but that means that an is contained in the a coin of radius epsilon. Oh, but this was true for all n greater than or equal to big N. Hey, this tells me that this a coin of radius epsilon contains the tail a greater than or equal to big N. And that's what we needed, right? This implies a dot converges to a. All right, so that's half of our proof. Now we want to go the other way. We want to show that if there exists an S sequence that converges to A, in which eventually the terms do not equal A, then A actually is a limit point. Okay, so let's assume, conversely, assume A dot converges to A, and A dot is an S sequence. Okay? Which eventually does not equal A. So eventually does not equal A. Okay, now because A dot is an S sequence, and of course we want it to converge, right? Yeah, we have that over here. Because A dot converges to A, this tells us that every A coin contains a tail. Of A. Now what is it we want to show? We want to show that A is a limit point. So to show that A is a limit point of S, we need to show that every punctured A coin contains an element of S. Okay, so if we want it to contain elements of S, well, we know that this sequence A, right, A dot, entirely consists of elements of S. So if we can show that every punctured A coin is going to contain elements from this sequence, then we're done, right? We have points that are completely in S. But we just said every A coin contains a tail of A. Which means every A coin is containing elements of the sequence. Okay, now if it contains elements of the sequence, the only thing we're really worried about is, well, what if they're all A, right? And if I then puncture it, I come over here and I get rid of all the A's, well then maybe there's no terms from S left. And this is why we have this extra condition, right? Which they eventually do not equal A. So since eventually A dot has no terms equal to A, its tails, or well, some of its tails, right? Its tails, we'll say, will eventually have non-A, right? So not equal to A, non-A elements of S. But this implies, thus, the punctured A coins, so we get rid of the A, will still contain elements of S. Okay, so the punctured A coins are the A coins, but they miss the point A. We know that the A coins contain the tail of A dot, which means they contain elements of S, as long as we don't throw them out. But the only thing we throw out is A itself. And eventually, the terms in the tail are not equal to A. The terms in the tail are other things. So that tells us that the punctured A coins are going to contain non-A elements, but those non-A elements are all coming from this S sequence, and so they're elements of S. Thus, or hence, A is a limit point of S. And this finishes the proof. All right, so this is why ultimately we want to talk about limit points as if they were limits of sequences. It's because they are. Okay, and if we go back to the previous one, right, this limit point characterization says, okay, a set is closed if and only if the set contains its limit points. But what are the limit points? The limit points are the limits of these S sequences, right? Even these special ones which don't eventually equal the point. So you're closed if your sequences of points that converge to A are actually contained in the set, right? So if I take S sequences, they converge to something. The convergent points, the limit points, have to actually be in S. Okay, so that's what closure has to do with limits, right? When you're closed, you contain the limits of your sequences. Okay, we're going to do another characterization of closed sets in terms of Cauchy sequences. Okay, and this should not be very surprising because we know that Cauchy sequences have limits. Right, so this should actually be a pretty natural thing to write down. Okay, so the theorem is that closed is equivalent to containing the limits of Cauchy sequences. Okay, so what do we mean here? If I have some subset S of R, S is closed if and only if the limit of every S Cauchy sequence. So I mean here now, it's Cauchy sequences, but the terms in the sequences all come from S. So every S Cauchy sequence, okay, it's a Cauchy sequence, so it has a limit. I can ask where that limit is. And if S is closed, then it always has to be the case that these limits is an element of S. So an example that we've seen already in this course is you take this sequence, 3, 3.1, 3.14, 3.141, 3.1415, 3.14159, etc. This is a sequence of rational numbers, and it's a Cauchy sequence. Okay, so this is a Q Cauchy sequence. And the sequence converges to pi, which is not a rational number. So this is an example of a Q Cauchy sequence that does not converge in Q. And so by the above theorem, this implies that Q is not closed. Okay? Of course, there's lots of ways of seeing that fact, but this is a very straightforward one. Okay, so one more characterization of closed sets. And in some ways, this gets us as close as we can get to how you probably wanted to think about closed sets from the beginning, right? We wanted to say, oh, if it's not open, then it's closed. And that's just not true. But what is true is the following theorem, which is that open sets and closed sets are complementary. Yep. So they say nice things about each other. Okay, so the statement is that if I have some subset S of R, then S is open if and only if the complement of S is closed. Okay, so recall if I have some set U and I take some subset S, then if I take all the elements in U that aren't in S, that's called the complement. Okay, and so if S is open, then the complement is closed. Okay, and because the complement of a complement is the original set, we could also write down here that S is closed if and only if S complement is open. Okay, fine. Well, now that characterization is going to allow us to translate statements about open sets into statements about closed sets. So let's do a theorem that is sort of the analog of a theorem we wrote down for open sets. We're just going to have to change the order of things. So closed sets are preserved by, well, let's jump back to when we talked about open sets. We were able to show that if you had finite intersections of open sets, that they were open. We were also able to show that if you had unions, any union of open sets, that it remained open. So what happens with closed sets? Well, it's actually just going to reverse. So closed sets are going to be preserved not by any union, but by finite unions. And not by finite intersections, but any intersections. And you'll see here in a second why you get the flip. Okay, so let's say that I'm going to prove, say, that finite unions of closed sets are closed. So I'm going to let S1 through Sn be closed sets. I want to show that the union over all these closed sets is closed. However, by the previous theorem, it's enough, if I want to show that something is closed, it's enough to show that its complement is open. So let me take the complement of this set. Now the complement of a union, by De Morgan's law, is the intersection of the complements. So this will be the intersection of the complements. Now each of these sets Sk was closed. So if I take their complement, each of these sets is now open. And by our result on open sets, if you take finite intersections of open sets, it's still open. So I have here a finite intersection of open sets, and so this entire intersection is open, which tells me that the complement of the original union is open, which tells me that the original union is closed. So this implies that the union of the SKs is closed. Okay. And the intersection property is going to work the same way. All right, so if I have an arbitrary collection, so if I is some indexing set, and I have S alpha, as alpha runs through I, is a collection of closed sets, then, well, if I look at the intersection over all alpha and I want this to be a closed set, but let me take the complement of it. Again, using De Morgan's law, this will be the union of the complements. And once again, because each of these S alphas was closed, I know that each of their complements is open. And because I know that a union of open sets, right, any union of open sets is open, then this union is open. And so, since the complement of the intersection is open, the intersection itself has to be closed. So that's pretty sweet. All right, so very often you don't really want to prove things about closed sets. You instead want to switch back to the world of open sets where maybe you've already proved something similar. All right, well, that's enough for closed sets for now. In our next video, we're going to go a little bit further and talk about compact sets. We'll see you next time.